Hello.
Hello.
Yeah, can you guys hear me now?
I can hear you.
Hello.
Okay.
Um,
Let's, since today is the first time, so let's wait, we'll wait for a few more minutes to see if there are any latecomers. Okay. I request that at least in the beginning, you turn on your video just so we can all see each other's face once.
I don't have a webcam. I'm on
Ah,
desktop right now.
okay. Then I guess we can't see you. So who was that? Who said that he does not have a webcam?
Uh, yeah, that was me.
It was who?
Yeah, Argodeep, me.
Argadeep. Okay. That's correct. You're the only one now.
My laptop is out of service right now, so once it's repaired, then I can.
Is Zubin, I've asked everyone in the beginning to show their face so people can see. After that, everyone is welcome to stop the video. I mean, I don't mind stopping my video either. I mean, also, but if I stop my video for some reason, the whole screen pretty much goes blank for me. Okay, so a few etiquette rules. Yeah, I suggest that I would like all of you to mute your mic, except when it is necessary. I mean, I don't mind being interrupted. Okay, as soon as you have any question. Okay, just to avoid background noise and sometimes kind of feedback. So I request that you do that. Zubin, okay, Zubin showed his face and then he disappeared. Okay. So let's see how many people are there. 1, 2, 3, 4, 5, 6, 7. Oh, 2 people have entered the waiting room for this meeting. What does that mean?
I think you'll have to click on something to let them.
There is some more people waiting to be admitted. Okay. Okay, I think it's time to start. Hey, for people that I just admitted, can you just to turn on your video briefly to say hi to the class, to everyone in the class, if you don't mind. Shivang and Sahil.
Hello.
Hi.
Hey, hi.
You can't see Ardeep because he's does not have a camera today. Shivang, can you hear me? Okay, good. Let me share my screen. Before I share my screen, yes, yeah, as I was telling everybody that I'd like people to keep their mic in mute state, but except when you want to ask questions. Okay, so you can turn unmute and then ask questions, and I'm okay to get interrupted at any time during the lecture. Okay, now I have you must have visited the movie page. Zubin, have you uploaded the form?
Yeah, it's there on the movie page.
Okay, so there is a form that Zubin has created and uploaded it, which just asks you to get some background about your thing. You are an MSc, BSc, DSc, which a program you are in, and also if what your background is in terms of the courses you've taken. It asks for a few courses. Now, see, I have not made logic as a requirement for this course. as long as you have had, although, it would help if you had logic, but I plan to do a quick 2 to 3 lecture recap of logic. So if you have, that is one of the questions on the form as well. It asks you a whole list of questions. With the, but I think you should have at least had a discrete math course, okay, which I presume all of you have had. Shake your, so which I presume that all of you have had. So with that and logic, course. So, but nonetheless, you fill out that form. So I'd like to know who does not have logic background, and what the kind of logic background that you need in this course is not that you need to have understood completeness proofs, compactness proofs of logic, full first order logic and so on. We'll be using mostly propositional logic, which you would have got exposed to in a discrete math course. But nonetheless, I will be doing a recap of first order logic, because it will be useful for you to know. And what you need is, you need to be comfortable enough with logic to be able to use propositional logic with quantifiers, okay, to model things, okay, and that you need to be comfortable with. And some concepts like, oh, sorry, somebody is, yeah, I should keep a watch on. Somebody was waiting, okay. So yeah, that's what you need. So that's why I will, after today's class, and possibly tomorrow, I will immediately get on to giving that recap of logic. And we're planning to introduce you to a tool that I encourage you to experiment with. This is Z3, which is a SAT solver, which kind of it is fun to do things in logic, and we'll give you some exercises and so on. So to get to become comfortable with modeling and experimenting with some basic concepts such as satisfiability, validity, and those kinds of notions, and how you can share. Yeah. Was there a question? Okay. So when there is, well, yeah, yes, okay. I guess when there is a question, you will have to unmute and then interrupt me. Or you can keep your video on and you can raise your hand if you wish. So let me share my screen. Are there any questions about the prerequisite? Okay, so so if not, then I will share my screen. Yeah, if you can't screen, if any of you cannot see my screen, just yell, okay? If not, I will assume that all of you are able to see my screen. Okay? Yeah, by the way, this, so the default is Zoom, okay? It is the class will be on Zoom. The video, oh, I have to, gosh, I forgot to. How do I? Yeah. Yeah, I had stopped recording. Okay, so I'll start recording. Share again. Okay, so as I was saying, the default is Zoom. Doing it on Zoom, but as you can see, I've also turned on. I mean, every lecture will be recorded and will be uploaded on on YouTube, and I'll give you details of that. How you could go back and then listen to the recorded lectures. And it is, as you can see, it is also being streamed on YouTube. Okay, so we have been generally asked to do that as the bandwidth requirement on YouTube is lower than apparently on Zoom. But if you're having bandwidth issues, then you should ask me for if you need YouTube. I still haven't figured out how exactly to get the link for that I will do, okay, by next time, okay. And how do I want to make it full screen. Let me make it full screen. Okay, so let me get started. Zubin, do you want to add anything? By the way, I mean, Zubin is the TA for the course. Okay, so he'll be doing a lot of the demos of the tools and making up the exercises, and he will be even grading. So be nice to him, and you can take his help as well. Okay, Zubin, do you want to add anything?
No, nothing right now.
Okay. So I'll start by motivating, why model checking, why study model checking. So you have nowadays embedded systems, okay? Which embedded systems are things that are implemented using a combination of hardware, software, and firmware, which more and more their complexity, they are becoming one of the most complex parts of real life machines. Okay, and can you see the whole screen?
Yeah.
Okay.
Okay.
Yeah, and they have generally become very ubiquitous. And these embedded systems, they typically are reactive systems that react to the internal state and external inputs, and they control more and more very critical parts, critical functionality of these kinds of systems, and therefore the importance of their assurance is increasingly getting more and more important. That is, if there are bugs in these systems, they can be life-threatening, or can lead to a lot of catastrophe, both in terms of money and life. And therefore, people are wanting a better and more foolproof methods to give assurance that they work correctly in practice. Okay, so what are the traditional methods that are used? They're mostly based on simulation and testing, and that's the dominant method. But simulation and testing, there are disadvantages. Okay, so firstly, they can only show a presence of bugs. In other words, they do not guarantee 100% coverage. Although there are testing methods that do give some coverage assurances, but it is impossible by the nature of testing and simulation that to be able to say, show absence of bugs. Okay, and they are also quite expensive in that, because they, you'll have to keep running on actual inputs, and so they are labor intensive and costly. So people are in engineering, software engineering and other hardware and software engineering and practice. They are always looking for better methods, and in the ideal case, can we have, to have automatic methods that can guarantee 100% coverage. That's the holy grail. Okay, whether you can accomplish that or not is a different question, but it is always good to try. And formal verification, which is a compendium of several methods based on logic and automata theory, is one such approach that can, in principle, guarantee this 100% coverage, at least for the properties that it is able to verify, that the method can guarantee that it is true, that the properties are met by the system for all possible behaviors. Now, model checking is also one such very popular technique, which is increasingly being accepted in practice. Okay, so, and that is what the subject matter of this course will be. And just to show that this is something, a subject matter that is also has depth, technical depth, I want to just mention that side, that this, by the way, model checking, the first paper where about this method was published in 1986. Probably simultaneously, by Emerson and Clark in one paper and Safakis in the other, and this was cited for a Turing Award in 2007. Okay, most of this work, at least when it started, was done in US by Clark and Emerson, when Clark was a professor at Harvard and Emerson was one of his PhD students. Clark later moved on to CMU, where he is an emeritus professor, I believe, and Emerson is in Texas, Austin. Safakis is a French computer scientist, and he continues to stay in France. And as you can see in the citation of this award, with this award, the contribution that the award was given for was not only to invent the concept, but later to make this technique highly effective verification technology that is currently widely adopted in the hardware and software industry. So it is not only has had, it was a theoretical impact, as well as it has impacted practices as well. Okay, so one of the kinds of, I showed all these big, bullet train and things. So let's get to, to somewhat, real things, that what exactly they kind of systems and properties that model checking is able to verify. So here's an example. I mean, a typical example that is always used for model checking: a controller that controls the traffic lights at an intersection. Okay, so what are the kind of property that you want to verify? This traffic controller can be signal controller can be quite complicated because it can sense. Of course, it has to change the lights in a way that it does not in certain safe manner, but it may also look at whether there is cars on either side and then do fancy things. So this can be quite reasonably complex. So the kind of properties that we're looking to verify for this are that the traffic lights should never be green. The two traffic lights be green at the same time. Okay, this is something an instance of property that's something bad does not happen. Okay. So another is this controller for traffic controller may be implemented in hardware and or combination of hardware and software. So let me then take another example of which is purely hardware, which is just a kind of digital synchronous digital circuit implemented in terms of logic gates and flip-flops, which are state holding devices denoted shown there by A and B. Okay, so what this says is that the okay, so a property that you might want to verify once again, it is something bad does not happen, that the counter value, this is a mod 4 counter, okay, counts from, and it can be reset at any time. It starts from and then it keeps incrementing the count which is stored in AB, and it's a mod 4 counter, so the counter value should always be, less than or equal to 3. Okay, so that's another kind of system. So then you can also have purely code software, okay, and this one, for example, this is a it has a while loop and it's not terminating, and it starts with the initial state of 0, 0. So one of the things that you might want to prove is you may notice that whenever you are at location 3, that the y is always greater than or equal to x, holds good. Okay, that is something that so this is kind of an invariant property inside the loop. Every time it is true when you enter the loop first, and then every time you go around the loop, it is true as well. So these are properties, like I said, something bad does not happen as per your expectation. You can also prove that eventually something good happens. This is of a different kind. For example, so it's also true, if you notice for this thing, that while x is always not 0, but x, because you're doing a mod 3 operation here after incrementing, x is always circulates, okay, between 0 and 2. So you can state and prove a property the kind that x is equal to 0 happens infinitely often. That is, every time x is equal to 0 is followed by eventually followed by a state wherein x is 0 again. Okay, see, this is a different kind of property. All the other 3 properties that I showed was that's something that you expect to hold good all the time. So here it is something called where you expect to happen eventually. Okay, so. And then you can have concurrent systems, okay, multi-threaded systems, where you have several processes. Now, for example, this counter, this mod 4 counter hardware is also a concurrent system, in the sense the flip-flops are incremented at every clock tick, and they happen simultaneously, but this is more synchronous because it is guided by this clock, whereas here this is a more asynchronous system, where there's no global clock, okay? And the ordering of the events is determined by a scheduler that is part of the operating system. So the kind of concurrency here is slightly different than the one that you saw in the for the hardware, and this is more asynchronous. So those are also the kind of systems that you want to verify. Now for this particular program, you may want to verify a property that the program has no data races, okay, which is usually not a good thing to have. So these are the kinds of systems, typically the kind of systems that we are interested in, and the kind of properties, okay? So these are called, properties, temporal properties, okay? These, because they state the, properties that make statements about the state of affairs distributed over time, okay? With the notion of time, is abstract, okay? So yeah, so model checking is kind of the focus of model checking is to verify these kinds of systems and properties. Okay. So what the kind of systems that we will not, at least in this course, not is something like this, where so you have where the time is continuous. I mean, the state ranges over real values, and time is also continuous. Okay. Now, model checking as an approach can be used for such systems as well, where the time is continuous. But in this course, we will be focusing on discrete systems where the time is discrete as well, and the state is also ranges over the discrete values. Okay. So of course, as you can see, the kind of systems that we want to verify, at least in their form, they're all quite different, heterogeneous. So in order to develop a theory and a tool for this, and a technique and a tool for this, what you need to have is, you can't be verifying each of these things in its own form. You need to have, by the way, I mean, as I've said, so this model checking is an instance of formal verification. Therefore, so it is, yeah. So whenever I just want to emphasize the fact that it is to distinguish it from testing it. Whenever you say something is verified, we want to be, the method has to ensure that it is verified for all possible behaviors of the system. Okay, so that's why. So yeah, so we need, getting back to the point that I was making, we need a common formalism for modeling these systems, so that you can develop the theory as well as the technique, based on that. That is one thing that we, that we need, and that's what I was making the point about here. So need a common formalism to model all those the kinds of systems that are of interest to us. Okay, and what we'll be using is something called transition systems, which we will define formally. Okay, and also we need an expressive language logic to specify the properties of the kind that you saw in the previous slide, to formalize, to express those properties in. What we're using will be what are called special purpose propositional temporal logics. Okay, to specify the property. So we'll be looking at different temporal logics that model checking methods are able to solve the verification problem for. So given these two things, then and then the third component, of course, you need efficient algorithms to automatically check that these properties that are expressed in this, the property that is formally specified is satisfied by the transition system, which models the actual system for which you're trying to prove. And that's what this is. In logic, this is defined as this, that M is a model, so M satisfies is this property, okay, for all behaviors. Okay, so that's the these are the three things, and this will be the essence of the three aspects that we'll be looking in the course. Any questions? Okay. Okay, before I elaborate these three things, I want to briefly mention other powerful verification methods. As I told you, formal verification is one of the methods. The model checking is one among several formal verification methods. So these are, I'm talking about three dominantly used formal verification methods. You must have, I don't know if how many of you have heard about static analysis or abstract, what is formally called abstract interpretation. That's also a very automatic method, very scalable, much more scalable than model checking, and it is much more widely used than model checking. Okay? But there are two restrictions over model checking for this abstract interpretation, and that is that it is limited in terms of the kind of properties that it can verify, and then the other one is it is a method that is imprecise in the sense it can give false negatives. Okay, but it is highly scalable, and a lot of it's very widely used in software industry. So and the other one is it's called theorem proving, where you have mechanical theorem provers that are able to mechanize proofs of properties in very powerful logics, not restricted to temporal logics that model checking is able to deal with. Okay, so that's why this is perhaps the most powerful and most general in terms of the properties and the kind of models that you're able to handle, that it is able to handle. But it is very interactive. It's the least automatic of all the three methods. Okay, so these methods, as I said, the two axes where they differ are the degree of automation with which they are able to prove properties, they're able to verify, and the expressiveness of the class of properties. I mean, expressiveness of the properties, and that is, in other words, the class of properties that they are able to verify. Okay, so model checking is somewhat in between abstract interpretation and theorem proving. It is certainly able to verify more properties that are more expressive than abstract interpretation. It is able to do temporal logics, properties that are expressive in temporal logics, or all a kind of automata. I mean, languages that are recognized by a certain kind of automata. And but it is a lot more automatic. Actually, it is completely automatic for the temporal logic that it is able to handle. and since that problem, the model checking problem that I showed for finite state systems is decidable, okay? And therefore it is completely automatic. But these are very hard problems, and therefore in practice it may not scale as much as abstract interpretation. Okay, but so here's the big but. So there was a period when in the last 10 years or so, meaning now 10, 15 years, okay, there have been such several breakthroughs in when it started out in 1986. Certainly for 10 years, for the first 10, 20 years, it was very toyish. Okay, model checking was only able to handle a few hundred of states maybe. Okay, and so everyone was about to give up on model checking, and especially industry was not that keen. Okay, starting in 2000, okay, there were several breakthroughs. One among them is breakthrough in techniques of Boolean, checking Boolean satisfiability using SAT solvers. There were several breakthroughs since 2000, from 2001 to 2010, that happened in SAT solving, and other very base techniques that were primarily aimed at scaling model checking to larger systems. Okay, and that changed the focus completely. Okay, and so to the extent that now they are there's a lot of interest in several software and hardware companies, and the kind of application that they are being they're being applied to is also branching out. Okay, typically, or even now, the dominant application is embedded systems and hardware software systems and concurrent systems, but they're also being used now for verifying properties about search engines, about biology, some aspects of computation biology, and even machine learning algorithms. So there is significant interest, is what I wanted to, the point that I wanted to make. Okay. Okay, so here's the brief outline, of the course. So first, a few lectures will be, will focus on how to model systems using and define what a transition system is, and what a Kripke structure is. This is some extensions to transition systems, and how they can be used to model at an abstract level the kinds of systems that we are interested in, the kind that I showed you earlier in terms of examples. Then we'll start, we will talk, we will formalize the kind of properties, especially introduce temporal logics, but we'll also be introducing these properties that, that are characterized by these temporal logics can also be viewed as languages over predicates, okay? Certain kinds of languages that are recognized by certain kinds of automata, okay? So there is kind of a duality between, viewing these as formulas in temporal logic, as, or as automata. So therefore the approaches are, so the theoretical approach is, there's also, you can view model checking, there's automata theory based approach as well. But the dominant method that is used is one that is based on what are called symbolic logic, and specifically SAT solvers. By dominant, I mean that is the one that is made inroads into practice, and therefore the emphasis of this course will be in modeling these systems in terms of logic, as propositional logic and the transition systems, and specifying property as in logic, the temporal logic, and then the methods will be model checking methods will be algorithms that branch that is assumes that you are using a logic to do it. Okay, then of course we will be introducing several tools. Okay, so that are typical of the state of the art tools that are used in practice. There'll be some. We get a chance to do some tool exercises, and I will be. We'll also be looking at a few techniques. Okay, that have now matured and are matured enough that we could be taught in class that are were critical in scaling the symbolic model checking method to large systems. Okay, by large I mean now it is measured in terms of the number of states. Okay, that these systems can range over. So now if the number is of the order of several tens of millions, it is no sweat. Okay, for model checking methods. We'll also be, time permitting, looking at how the same methods which employ based on symbolic logic can also be viewed as in terms of as language inclusion problems. Okay, language inclusion problem in certain kinds of languages recognized by certain kinds of automata. Okay, so but even these methods, automata-based methods, eventually have to rely on SAT solvers in order to be able to scale, and that's why the focus here I'm keeping it on symbolic logic. Okay. Yes. Okay. So this is a good time for me to pause and maybe ask. See your faces again to make sure that you're all alive and kicking. And if you want to ask questions, you can, let me, yeah, you can show your faces and do you have any questions? Hello? Any questions? Are you guys there?
No, sir.
Huh?
No.
Ah, okay, fine. Okay, so then I will go back to full view. Yeah, here's the way that I'm structuring the grade distribution. There will be several written assignments, okay? So that'll be 30%. Written assignments, there'll be pencil and paper, looking at pencil and paper things where you will solve things on a paper, so written assignments. And actual doing things using, these tools will be, and then there'll be 2 quizzes is what I've said, but I typically sometimes, do a midterm, and the final one will be a small programming project. Now that is something that, if that's why I've also asked one of the questions in my in that form is if you're, what your programming skills are like, and if you all don't mind doing. Implementing some small model checker or some method that we cover, model checking method algorithm that we cover in the class as implement that using a SAT solver, that can also be an option. Okay, so I want your feedback on that. Okay, so yes, so that is pretty much, yeah, that's the thing. And here is the reference textbook. You said there is e-textbook. There's one in the library. Obviously you can't get to the library. So what I have done is I have bought an e-textbook version. I took the version in the library and I kept it to myself at home. And I have this e-textbook. Works as you need to log in. So and I'm saying that I will provide you with the link, the login link, and the user ID and password, and you can use the textbook as a reference one. And since it has to be timeshare, I'm suggesting that we make up some kind of a sign-up sheet, or at least that lets you, when you're busy using, okay, because this one can only be only one person. At most, one person can be using it at a time, and therefore, so I'm thinking of having some kind of a sign-up sheet. Okay, so that is some of the things. Okay, so how is the, in terms of the technical issues, are you all able to hear me well? And the bandwidth at your end is all well and good? Is this, or do we need to make some adjustments? Okay, so I will take, since there is no answer, I will take that as that you're all okay with Zoom, and you don't need the YouTube version.
Yeah, I think a lot of people are saying it's okay in the chat.
Okay. Yeah, I think I will also, I mean, we can do this. Yeah, the YouTube version is, the disadvantage is that it can't be interactive. Okay. That is one thing. But I mean, I could, once I figure it out completely, I can provide you the link on the YouTube, on YouTube as well, if indeed you're facing any bandwidth issues. Okay.
I think it'll be nice to have YouTube so that we can check the lectures later on if we need it.
No, that will certainly be there. Okay.
Okay.
I'm recording, by default, I'm recording it on Zoom, and I will be uploading it on that. That part will be there.
Okay.
Only the live streaming part, what I'll have to do is every time, I turn on the live stream, it generates a link, okay? And then the YouTube link, and I'll have to publish that link, okay?
We can actually see a live on YouTube link on Zoom, so we can access it from Zoom as well.
But then I don't know if that will save you any bandwidth, okay? Maybe it does.
Okay.
Maybe it does. But no. But won't you need? Well, then you have to use it through Zoom. I don't know if that gives you any advantage in terms of the thing. I don't know.
That's
what I was thinking was you don't need to use Zoom at all. Once I start the live stream, and then I give you the link, then you can only use the YouTube for live streaming. Okay. So that apparently uses less bandwidth, okay, than live streaming on Zoom, is what I've been told. And that's why that option was asked for instructors to be made available for the class. Okay. Yeah, so I will do that anyway. So people who want to use that can use it. Yeah. Okay, so we still have 5 more minutes. So let me start with my next module. Maybe I should show you. I have a partial schedule for the course. Okay. At least the next few lectures I have made, I will complete this spreadsheet and I will upload it so that you will have an idea. So yeah, first after the introduction, so I will start with a little bit with modeling, okay? And then I'll immediately switch to doing a recap of logic. By the way, I mean, since they're not, you know, this is still not, let me see. I hope. Yes. Okay. No, I was. Yeah. Then I think you fill out the form rather than asking you a show of hands for how many people have taken logic course, etc. So this is my way to actually, before I get too much into the subject matter, to actually do a quick recap and even have you start doing some Z3 exercises so that you will get comfortable with doing things with logic, okay? Propositional logic. So I think that should be there. Even if you don't have, haven't had a logic course formally, I think it should be doable, but that's something that you will have to figure out, okay, and then decide on. And if you have any questions, if you don't have a logic course and you want to take the course anyway and then discuss, you can send me an email, okay? Yeah, let me move to my second module today, and I will do as much of this. Sorry. Okay. Okay, so this module, the outline for this are as follows. So we will spend some time, trying to talk about what are the things that need to be captured in inside a model. Okay, because there is, yeah, as you will see, there is fair amount of freedom in how you want to define the model, and what things you want to include in a model when you're really doing things, trying to apply it to real systems. Okay, some of these aspects will I'll cover. Then I will formally define what a transition system is, a kind of crypt key structure. Yeah, and then talk about two concepts that are very critical to modeling and abstraction and non-determinism. Okay, and I'll discuss a few examples of modeling, starting with software and hardware, and then talk about cryptic structures and behaviors of transition systems. So that's the outline. I don't think I'll be able to cover the whole thing, so but let me how far I can get through. So as I said, we need, so what transition systems, the purpose of transition is we need a common formalism to model the diverse kind of things. And this is, you've already seen. So what are the things? Okay, you saw these systems. Okay. So obviously, if you look at the property, let's say the kinds of things that you want to model. Okay, say developing a model is part of what is called requirements engineering. Okay, so you'll have to, given a system that you want to model and the kind of properties, an engineer gives you a system and then he gives you what he cares about. Okay, that he wants to prove for that system. Usually, it is the properties that determine the kinds of properties that you want to verify that determine what you want to keep and what you want to throw away in that model. And that exercise is what is called requirements engineering. Okay, but if you look at these properties, okay, yeah, I think in some cases where I want to raise a question, there is an advantage that keeping this unmuted, I guess, so then so that I can immediately ask you a question. So what is, given these systems and these properties, what is something that you certainly want to include in the model?
Excuse me, can you repeat?
Yeah, so I'm saying, so look at the systems and the properties, okay? So I'm asking the question, what is something that you should have as part of a model, okay? So I'm trying to motivate what should be the components of what you should include of a transition system, okay? What is something that all of these things talk about, okay? We look at the property. They talk about, they express something about the state, about the state of the system, right? So for example, here, this is saying, okay, this particular light should be when it is green, both cannot be in green. So there is something called, all of these systems, they maintain certain states, okay? And that state is changing over time. So those are the two things. So you have to, be able to talk about state, okay? What a state of the system is and what are the components of the system. I mean, what should go into the state. And the other thing is there is transition also of the state over time, okay? Now the notion of time can be as abstract as you want, okay? Now here the state changes, okay? So in this case, whereas in the case of, for example, in hardware, there is an explicit clock which you may not keep in your system, but but that is what the change of the state of the clock is what defines the state. So there are two things, and even after you define what are the things that are relevant about the system in the state that you want to keep, there is you have to define what kind of values that you at what level that you want to define them at. For example, what I'm getting at is, for this hardware system, if you look at, if what you really are interested in verifying hardware, that hardware really is can be implemented on a board, and the state will be is represented as voltages, okay, in your on certain devices on the thing. But model checking is not about proving. So the voltages will be some real values, okay. So, but that is not the level of detail at which I'm talking about. So the kind of properties that you saw, what, since we assume that we are only interested in discrete values for the state, so there is a certain level kind of abstraction that abstraction means throwing away certain details. In this case, we certainly are not interested in the actual values of voltage and things, but what we care about is whether that voltage level is interpreted as a 1 or as a as a 0. And now maybe ones and zeros, you may make a decision as 1 and 0, but maybe there are multi-valued logic, okay, multi-valued states that you want to reason about, okay. In any case, this is one thing that you will always decide in practice, okay. So what are the relevant part of the state, okay, so that we usually call as state variables, and what is the domain that you have to pick, that you have to use for representing the values of that state variable, okay. And of course, yeah, so this is what I'm trying to say. And of course, the other thing is what exactly time, which is represented as a transition of a state, capture for the system, and how you should view the change, okay, of the time at what level that you need to view it at. So as I was saying, so our systems always have a state, and these states are, could be various things, okay. If you're verifying a program, then they can be the values stored in program variables. If you're verifying registers, so there will be the bit states, if that's the level at which you want to verify. It can be in flip-flops. I say these things because model checking has actually been used, by the way, to verify transistor level circuits as well, okay, believe me. So where if you're verifying something at the transistor level, not at the logical level, then you may want to keep more things, more than ones and zeros, okay. So this is one. So we have a state, and the state has several components, and they are called state variables, okay. And we need to decide on a domain that each of these state variables will be ranging over, okay. That is one. Yeah, as I said, in this course, we will be focusing only on discrete domains, okay, state variables. The second thing is, the model has to support change of states over a time, and the time doesn't have to. You can, the granularity of time, you can decide, okay, and it may be even kept abstract, okay. So that is embedded in the notion of what exactly is a transition. I mean, that is captured by the notion of transition of the states in the transitions system. And the granularity is something that you can decide based on at what level of how you want to capture time. Okay. So once again here, like I showed the pendulum example, the time there is continuous, and you might want to model and then verify asymptotic behavior, in which case you will have to deal with continuous time and asymptotic behavior. So it can be discrete, but the granularity can be different. Can be your choice. So another assumption that we'll be making throughout the course, as for the methods that we will be discussing in the course, will be focusing on discrete time transitions. So here is a formal definition of what a transition system is. Yeah, I used Kripke structure there. Okay, Kripke structure is pretty much a transition system, except it has one more component that we will that I will get to. So now I'm defining a transition system. It is a tuple, a three tuple, which has a set of states, that the universe of states, and the set of initial states. Okay, set of initial states that the system can start in, and then a transition relation, okay, which relates, which captures the state transition. Okay, so it's a pair of states. The transition relation is a set of pairs of states, and so a pair, belongs to T if S, the second component, is a successor of the first component. And that's how it captures the state transition. Okay, so let's take an example. So suppose, okay, we want to model this code at a level that is detailed enough to capture the property that I mentioned. That I mentioned about. In the previous slides. Okay. This is just a So before I do that, So what should be a state here? Okay. Of course, the property, if you recall, we wanted to prove something, that relationship between X and Y over time, right? So obviously, the state should have X, the two state variables, X and Y, okay? And you see, what should be a transition is the question, okay? In general, a program is a set of instructions already, okay? And you want to be able to, if you want to be able to prove the state of the program at every location, that maybe you have to capture even the locations at the level. But you recall the kind of property that I showed earlier cared only about what the relationship between these variables were at the beginning of the loop, okay? Every time at location 3. Therefore, you could have something, like this. All you care about is what the value is initially. This is actually a compressed of CFG, meaning control flow graph, okay, of this thing. Because I only care about things, a property at location 3. Therefore, I'm kind of merging all these statements into a block, okay, and I'm keeping track. So this corresponds to before I enter the loop, 0 location, and location 1 corresponds to when I'm at the head of the loop, which is where I want to track these the state. Okay, so the transition here pretty much corresponds to these two things. There's a transition from the initial state to the head of the loop, and then the body of the loop is captured by a single transition. Okay.
Sir, could you repeat what exactly are the states here?
Yeah, the states are the state has two state variables which track the X and Y. They keep track of what the value of X and Y are. Okay. So that's what that thing is. So I will show you. Yeah. So because, why did I choose that? Okay. I could have thrown away probably lots of other things, but my properties had, said something about X and Y. So I had to keep track of those X and Y at least. Okay. So yes. So the state is exactly this. Okay. So it has two components. That's why it is D1 cross D2. D1 is the domain corresponding to the values that X ranges over. D2 is the domain for corresponding to Y. So in this case, it is enough, to define these domains as I have shown here, because the values that these things range over are only X can range over only from 0 to 2, and Y can range over only from 0 to 3. Do you believe? Correct?
Yeah.
Yeah, because of the mod operations. Since also I'm interested only what happens here at location 3 after after the entire block happens. You can see that, of course, before doing the mod, X plus 1 can go to 3. Okay, X can go to 3, but then I don't care about that. I mean, I'm only tracking the values of X and Y here. So this domain is adequate. Okay? And my initial state is, an initial set of states here is unique because both of them are, both X and Y are 0. And the transition relation exactly correspond to the 4 transitions, the arrows that are shown in this graph. This is a graphical form, okay, where every node corresponds to an valuation of the state, okay? So every node here corresponds to a valuation of the state. By valuation, I mean the different possible values that the state variables can take, okay? Of course, yeah, okay. Now, there are, yes, some states missing from here. Have you noticed? So this, in that sense, okay. And anyway, so these, yeah, I mean, first I will ask the question, okay? So have you noticed that there are some, so the universe of states is S is D1 cross D2. So you can also have, S also includes the state 0, 3. And I haven't actually shown that here. So strictly speaking, I should show 0, 3 also, because that is also included in the universe of states. Why do you think I haven't shown that? Okay, because that state is never reachable. Okay, this program, at least in this transition system, never gets to that state. Okay, because of the way the transition relation is. As you can see, this R includes only these pairs of states. R here is a pair of pairs of states. I mean, a pair of states. Why? Because it has to map each state, I mean, a current state to the next state. So if you're in 0, 0, your next state is 1, 2. Okay? And that's why this element is inside R. Okay? If you're in 0, 1, also you will get to 1, 2, right? Because X gets X plus 1 mod 1, mod 3, and Y gets whatever the new value of X is plus 1. So that's why this element is there in R. And as you can see, this corresponds to the third element here, corresponds to this transition. I hope you can see my cursor.
Yeah, they can.
Okay, fine. And this one corresponds to this, okay? So the one subtle point that I want to make is 0, 3 is in the state of universe, but it is not reachable from by any sequence of transitions from this initial state, okay? So that's how, yes, that is what transition means. Any questions you have here? I want to stop here. So you can unmute your microphones, okay? and ask me any questions you have, either on technical questions on the subject matter or administrative questions or anything. Okay. Yeah. So before I leave, I want to remind you to fill out the form so that I'll get the background of people. And if you have any concern about the course, the course material, or not, having a logic background in symbolic logic, you can send me a note. If there are no questions, then I will stop here. If I can get, I'll have to, just one moment. I just want to, yeah, are there any questions? Hello?
I don't have any question.
Okay. Okay, guys, so I'll see you on Thursday, okay? Stop sharing.